In this lecture, we will basically discuss the fuel supply system for SI engine and specifically the working of carburetor and its design principles. Now, what is the function of engine induction and fuel systems in SI engine? Its basic task is to prepare air-fuel mixture in the requisite ratio, and the air is taken from the atmosphere and the fuel is taken from the fuel tank fitted in the SI engine. Now, from these two, that is from the ambient air and from the fuel tank, air-fuel mixture is prepared to meet the different requirements of the engine over the operating regime. Means sometimes we have the requirement of rich mixture, and on the other moments or transient operations we can require lean mixture. So basically this engine induction and fuel system is preparing the air fuel mixture in varying proportions so as to suit the requirement of the engine. In principle, the optimum air fuel ratio for a spark ignition engine is that which gives the required power output with the lowest fuel consumption, consistent with smooth and reliable operation. The relative proportions of fuel and air that provide the lowest fuel consumption, smooth reliable operation, and satisfy the emission requirements at the required power level depend on engine speed and load. Mixture requirements and preparation are usually discussed or mentioned in terms of air-fuel ratio or fuel-air ratio. The fuel metering system is designed to provide the appropriate fuel flow for the actual air flow at each speed and load. Mixture requirements are different for full load, that is wide open throttle, and different for part load operation. For the full load operating conditions, complete utilization of the inducted air to obtain maximum power for a given displaced volume is the critical issue. Whereas less than the maximum power at a given speed is required, efficient utilization of the fuel is the critical issue. At wide open throttle, maximum power for a given volumetric efficiency is obtained at higher, or you can say richer, stoichiometric fuel mixtures. Mixtures that are still higher or richer are sometimes used to increase the volumetric efficiency by increasing the amount of charge cooling that accompanies fuel vaporization, thereby increasing the inducted air density. At part load, or you can say partly open throttle operating conditions, it is advantageous to dilute the fuel air mixture either with excess air or with recycled exhaust gas. This dilution improves the fuel conversion efficiency for three reasons. The expansion stroke work for the given expansion ratio is increased as a result of the change in thermodynamic properties of the burned gases. Second, for a given mean effective pressure, the intake pressure increases with increasing dilution, so pumping work decreases. Third, the heat losses go to the walls are reduced because the burned gas temperature are lower. In the absence of strict engine NOx emission requirements, excess air is obvious diluent, and at part throttle engines have traditionally operated lean. When tight control of NOx, HC and CO emission is required, operation of the engine with a stoichiometric mixture is advantageous so that a three-way catalyst can be used to clean up the exhaust. The appropriate diluent is then recycled exhaust gases, which significantly reduces NOx emissions from the engine itself. The amount of diluent that the engine will tolerate at any given speed and load depends on the details of the engine combustion process. So in the spark ignition engine, a combustible fuel air mixture is prepared outside the engine cylinder. This process of preparing the mixture is called carburation, and this process is achieved in the induction system, which is shown on the slide. The carburetor is basically a device which atomizes the fuel and mixes it with air. Now, atomization means breaking up of the fuel droplets into smaller ones. So basically, carburetor is not only breaking up the fuel droplets into smaller droplets or particles, but also mixing it with air so that the mixture becomes homogeneous. The pipe that carries the prepared mixture to the engine cylinders is called intake manifold. Manifold is nothing but a complex pipeline. So basically, intake manifold is carrying the prepared mixture to the engine cylinders. Now during the suction stroke, vacuum is created in the cylinder, which causes the air to rush through the carburetor and the fuel to be sprayed from the fuel jets. Because of the volatility of the fuel, most of the fuel vaporizes and forms a combustible fuel air mixture. However, some of the larger droplets may reach the cylinder in the liquid form and must be vaporized and mixed with the air during compression stroke before ignition by the spark. Now there are certain factors which significantly affect the process of carburation. One is time available for preparation of mixture. Now the different processes which are necessary to achieve the homogeneity of the mixture are atomization, mixing and vaporization. And all these processes, atomization, mixing and vaporization, they require certain finite time to occur. Now in high-speed engines, the time available for the mixture formation is very small. For example, let us assume an engine running at 3000 RPM, and here the induction process will be lasting less than 0.02 seconds. Now because of this short time available, complete and efficient mixing, vaporization and distribution is difficult to achieve. Now the temperature is another factor which basically governs the vaporization process of the fuel. A high temperature results in high rate of vaporization. The temperature of the mixture can be increased by heating the induction manifold, but this would reduce the power due to reduction in mass flow, because by heating the density of the air inducted will decrease, thereby decreasing its mass flow rate. The volatility of the fuel affects the vaporization and distribution of the fuel. So the design of induction manifold affects the uniform distribution of the mixture among the cylinders and the constancy of its composition under variable operating condition. Now the design of carburetors is also affecting the process of carburation, because the optimum air-fuel ratio required by it varies widely over its operational range, particularly in the case of an auto engine. When the engine is idling, richer mixture is required due to dilution of the mixture by products of combustion. At full load condition, a richer mixture is required for maximum power. An engine generally operates at varying loads and varying speeds. Now, the engine at any load or speed condition have a particular requirement of air-fuel mixture which is quite different from the condition of other load or other speed. Now there are three different types of mixtures. the chemically correct or stoichiometric mixture. If we assume petrol or gasoline to be having isooctane as the major constituent, then the combustion equation is C8H18 plus 12.5 moles of oxygen, giving out 8 moles of CO2 and 9 moles of H2O. So C8H18 is basically the formula for the chemical formula for the isooctane. So if we calculate the molecular masses, then we can say in 1 mole we will be having 114 kg of fuel, and to burn that or to oxidize that we will be requiring 12.5 moles of oxygen, that is 400 kilograms of oxygen. So to burn 114 kilogram of fuel, the oxygen required is 400 kg. Now to burn 1 kg of fuel, O2 required is, that is oxygen required is 400 upon 112 kg. This is the unitary method which we have learned in earlier classes. Now you know that oxygen is present in air by 23.2% by mass. So air required to burn 1 kg of fuel is this, which is giving out value of 15.1. So you can say that as per the chemically correctness condition, the air fuel ratio is 15:1. We round it 15.1 to 15. So we can say 15 kilogram of air to burn 1 kilogram of fuel. Now the other air fuel mixtures are rich mixture and the lean mixture. Rich mixture is one which contains less air than the stoichiometric requirement. For example, air fuel ratio of 12:1 or 10:1 is said to be a rich mixture. Now the lean mixture is one which contains more air than stoichiometric requirement. So air fuel ratio of 17:1 and or you can say 20:1, they are known to be lean mixtures. Now the mixture requirement for maximum power is different from any other operating condition, and it requires air fuel ratio quite different from the stoichiometric condition. Similar is the case with the mixture requirement for maximum economy, that is minimum specific fuel consumption, and it is also a unique operating condition, and it requires air fuel ratio quite different from the stoichiometric conditions. Now figure on the slide show that the maximum power is obtained at an air fuel ratio of about 12.5:1. We know that the maximum energy is released when some excess fuel is introduced, so that all the oxygen present in the cylinder is utilized. If more fuel is introduced, then this would be disadvantageous, as large excess of fuel with the same amount of oxygen will result the smaller energy release due to partial combustion as well as formation of more carbon monoxide. Now we discuss the mixture requirement for minimum specific fuel consumption, that is maximum economy. Now figure on the slide show that at full throttle maximum efficiency occurs at an air fuel ratio of about 17:1. Maximum efficiency is obtained at a point where the mixture is slightly leaner than the stoichiometric air fuel ratio. The reason for this is the excess air required for the complete combustion of fuel when mixing is not perfect. Now due to lean mixture, the energy input will be less and the temperature rise will also be less. The lower maximum temperatures will result in lower specific heat as well as lower chemical equilibrium losses. If the mixture is made too lean, the flame speed reduces such that consequent large time losses overcome the benefits of improved efficiency with leaner mixture, and ultimately the efficiency starts decreasing if the quantity of air increases beyond a certain extent. There are basically two types of operating conditions as far as the quality of air fuel mixture is concerned. First is steady state operation, which basically includes idling and low load conditions, normal power range as well as maximum power range. So under steady state operation, we will basically study three major conditions. First is idling and low load conditions, second is normal power range, and third is maximum power range. Now transient conditions or unsteady state conditions, which basically lasts momentarily, are starting and warm up requirements, and the next one is acceleration requirements. Now basically carburetor is a mechanical device which is designed to serve the function of providing quantified amount of fuel so as to supply the requisite air fuel ratio to the engine at all speeds and loads for steady as well as transient conditions. The other function of carburetor include the atomization of fuel droplets, means breaking up of liquid droplets into smaller ones, as well as mixing it with air so as to obtain homogeneous air fuel ratio. Now here you have to keep in mind two things. First is the word meter the liquid fuel. Now metering means to supply the fuel in quantified amount, in measured amount. So basically carburetor is not supplying the fuel in unmeasured quantity, but it is supplying the fuel in measured quantity as per the requirement. The second important word is atomization. Now atomization means breaking up of the fuel particles into smaller one, so that the surface area of the fuel exposed to air increases and we get better homogeneity in the air fuel mixture. Now the engines are also classified as stationary engines or automotive engines based on their mode of application. In stationary engines, the objective is to have an air fuel ratio that gives the maximum economy, means lowest specific fuel consumption. In case of automotive engines which operate under variable speed and load conditions, the air fuel ratio depends on the condition of requirement of maximum economy or maximum power. Means there will be particular air fuel ratio for maximum economy and a different air fuel ratio for maximum power. Moreover, the air fuel ratio will vary slightly or significantly for transient conditions like starting, warm up and acceleration. But under all operating conditions, whether steady state or transient conditions, the exhaust emission should be kept minimum. Three main steady state operating conditions for automotive engines requiring different air fuel ratios are basically the idling and load condition, normal power range and the maximum power range. One thing here you should note that steady state operation means the engine is continuously operating at given speed and power output with normal engine temperature. Now idling and low load conditions. Idling means zero load, no load, and low load means we are referring to the load up to 20% of the rated power of the engine. Means if the engine is of a rating of 5 horsepower, then we can say from 0 to 1 horsepower we will consider under idling and low load conditions. During idling, the throttle is nearly closed, thereby restricting the air supply with consequent decreasing suction pressure. So the condition of low pressure gives rise to backflow of exhaust gases and air leakage from the various parts of the engine intake system. As the exhaust pressure is higher than the intake pressure, backflow occur during the valve overlap period at idling and part load operation. Now, due to this backflow, the amount of residual gases increases. Now, these residual gases expand during the suction process, thereby reducing the fresh mixture inhaled. So, the increased dilution causes the combustion to be erratic or even impossible. Now, these type of erratic or irregular and slow combustion basically yields poor thermal efficiency and higher exhaust emissions. This problem of dilution by residual gases gets aggravated, means it becomes worse at low loads and idling because the exhaust temperature reduces with decreasing load. That is, the density and hence mass of residual gases increases. Further, at low inlet manifold pressures obtained at idling and low loads, the dilution of the charge occurs due to air leakage around the walls. So the phenomena of backflow of exhaust gases or air leakage that causes the dilution of the charge. The air fuel ratios used for idling and low loads are made rich in fuel to obtain smoother engine operation. At full load, the air fuel ratio goes up to 12.5:1. Now question arises that how rich mixture improves combustion. The amount of fresh charge inducted during idling is much less as compared to that during full throttle operation. The presence of exhaust gases tends to obstruct the air and fuel. Now if the mixture is made rich, that is, it is containing more fuel particles, the probability of contact between fuel and air particles will enhance, which basically will improve the combustion. Now normal power range, or you can say cruising range. Cruise means the movement of a particular vehicle or automotive at constant speed, that is known as cruising. Now this normal power range or cruising range includes the load from 20% to 75% of the rated load. As the load is increased above 20% of the rated load, the dilution by residual gases as well as leakage of air decreases. So in this range we can focus upon fuel economy. As discussed earlier, maximum fuel economy occurs at an air fuel ratio of about 17:1. Normally the mixture ratios for best economy are very near to the mixture ratios for minimum emissions. Now the maximum power range, which includes the load from 75% to 100% of the rated power. Now as discussed earlier, the mixture requirement for maximum power is a rich mixture of about air fuel ratio of 14:1. Apart from providing maximum power, a rich mixture also prevents overheating of exhaust valves at high load and thus reduces the tendency of detonation. Now at high load, the heat transfer to the engine parts is higher. Enriching the mixture reduces the flame temperature and the cylinder temperature, thereby reducing the cooling problem and decreasing the probability of damaging the exhaust valves. Also, reduced temperature tends to reduce detonation. There is an elaborate arrangement for the enrichment of mixture in aircraft engines, as detonation can wreck the engine in a matter of seconds. Whereas in the case of automobile engine, this elaborate arrangement for enrichment is not required, because in these engines detonation is audible as knock and the driver can take corrective measure by decreasing the load or increasing the engine speed by shifting to a lower gear ratio. Whatever discussions we have done for these three steady state conditions, it was with reference to single cylinder engines. In multi-cylinder engines, the air-fuel ratio is slightly lower. That is slightly richer mixture, which is basically done to overcome maldistribution of air-fuel mixture in different cylinders, which we will discuss in next slide. In multi-cylinder engines, the carburetor supplies the air-fuel mixture to each of several cylinders. Suppose if an engine is having 4 cylinders, then carburetor will supply air-fuel mixture to 4 cylinders. Ideally, each cylinder should receive mixture of the same air-fuel ratio. But practically it is not possible. It is very difficult to achieve the ideal condition of same air-fuel ratio. In the carburetor, complete atomization and vaporization of the fuel is not achieved. Though we are designing the carburetor so as to achieve the complete atomization and vaporization of the fuel, but even then it is not done. Therefore, the mixture passing through the intake manifold generally contains a certain amount of petrol in the droplet form. These droplets have greater inertia than the gaseous counterpart, and hence whenever the direction of flow is changed abruptly, the droplets tend to continue in their original direction of movement, as shown in the figure on the slide. So consequently, there is a variation in the air-fuel ratio between cylinders. The outer cylinders are getting richer mixture as compared to the inner cylinders. Not only this, the existence of thin film of liquid fuel adhering to the inner walls to the intake manifold is another factor that contributes to this uneven distribution. Now, what remedies are adopted to correct this imbalance in air-fuel ratio in different cylinders? The mixture in the intake manifold may be heated to vaporize the liquid droplets, but this would reduce the mass of charge with consequent reduction in power output. Second option could be a rich overall air-fuel mixture may be supplied so that leanest cylinder receive the required air-fuel ratio, means correct air-fuel ratio, but then other cylinders will get richer mixture than what is required. Apart from providing a suitable mixture for steady running, as we have discussed, a carburetor has to provide mixture for transient conditions under which speed, load, temperature or pressure change rapidly. The principal transient conditions of operation include starting, warming up, acceleration and deceleration. The transient mixture requirements vary from that of steady running mixture requirements. It is because in the transient case, the evaporation of the fuel may be incomplete. The quantity of liquid fuel in the inlet manifold may be increasing or decreasing, and the distribution of the fuel to various cylinders may be different. As you all know that petrol is a mixture of hydrocarbons which are having different boiling temperatures. Means petrol is mixture of several hydrocarbons which are distilled at different temperatures. Now the hydrocarbons which have high vapor pressure and low boiling points are called light ends, as they are the volatile or more volatile components of the petrol. The hydrocarbons which have low vapor pressure and high boiling point are known as heavy ends, and they are less volatile. At starting or at low speeds or low loads, the engine temperatures are low, and therefore most of the light ends supplied by the carburetor do not get vaporized and remain in liquid form. Even a part of vaporized fuel may recondense on coming in contact with cold cylinder walls and piston head. That is why even when the fuel air ratio at carburetor is well within the normal combustion limits of petrol air mixture, the ratio of evaporated fuel to air in the cylinder may be too lean to ignite. Therefore, during starting, a very rich mixture has to be supplied. We can say air fuel ratio varying from 3:1 to 13:1, so that sufficient light ends, means vaporized petrol, are available for proper ignition. As the engine warms up, the amount of evaporated fuel increases, and then the richer mixture is not required as it was required for the starting conditions. So the mixture ratio should be progressively made leaner to avoid too rich evaporated fuel air ratio. Too high or too low volatility both creates difficulties in operation. If the volatility is too high, vapor bubbles may form in the carburetor and fuel lines, particularly when the engine temperatures are high. So this is the condition of cavitation. These vapor particles interfere with the supply and metering of the fuel and may disturb the fuel air ratio to that extent so as to cause the engine to stop. On the other hand, if the volatility is too low, petrol may condense on the cylinder walls, diluting and removing the lubricating oil film. Condensation of the petrol on cylinder walls also causes carbon deposits. You know that acceleration is nothing but rate of increase in engine speed. When we press accelerator pedal in four-wheeler, we are basically opening the throttle. The main purpose of opening the throttle is to provide an increase in torque. Whether increase in speed will take place or not, it depends on the nature of the load. The fuel evaporated in the intake manifold moves much faster than the liquid film formed on the induction system walls. Under steady running conditions, this does not cause any problem, but when the throttle is suddenly opened, that is during acceleration, the liquid fuel lags behind and temporarily the cylinder receives a lean mixture, whereas actually a rich mixture is required to produce more instantaneous power acceleration. So now, in order to compensate for the temporary leaning of the mixture and to provide rich mixture needed during the acceleration period, additional fuel must be supplied by the suitable mechanism. This mechanism is known as acceleration pump and we'll discuss in slides. A simple or elementary carburetor provides an air-fuel mixture for cruising, or you can say the constant speed range. Other mechanisms are provided for the other duties like starting, idling, variable load and speed operation and acceleration. A simple carburetor consists of a float chamber, nozzle with metering orifice, venturi and throttle valve. Float chamber is vented to the atmosphere so that atmospheric pressure acts on the surface of the fuel. The float and a needle valve system maintains a constant level of petrol in the float chamber. If the amount of fuel in the float chamber falls below the designed level, the float lowers, means it moves downwards, thereby opening the needle of the fuel supply valve. When the requisite level or say design level has been reached, the float closes the needle valve, thus stopping the additional fuel flow from the supply system. During suction stroke, air is drawn through the venturi. Venturi is basically a tube of decreasing cross section having minimum cross section at the throat. The air velocity increases while passing through the venturi and is maximum at the throat. Similarly, the pressure in the venturi throat decreases while passing through the venturi and is minimum at the throat. From the float chamber, the fuel is fed to a discharge tip, the tip of which is located in the throat of the venturi. Now the pressure in the float chamber is atmospheric, and vacuum means pressure below atmospheric pressure exists at the discharge jet. So because of this pressure difference, the fuel in metered, or you can say measured quantity, is discharged into the airstream. The rate of fuel flow is controlled or metered by the size of small section in the fuel passage. This is provided by the suitable choice of the discharge jet, and the size of this jet is chosen empirically to give the required engine performance. The pressure at the fully open throttle condition lies between 4 to 8 centimeter mercury below atmospheric. To avoid wastage of fuel, the level of liquid in the jet is adjusted by the float chamber needle valve to maintain the level a short distance below the tip of the discharge jet. The petrol engine is a quantity governed engine, means the quantity of air fuel mixture is varied according to the load. When less power is required at a particular speed, the amount of charge, that is air fuel mixture, delivered to the cylinders is reduced. It is done by means of a throttle valve of the butterfly type, which is situated after venturi tube. As the throttle is closed, less air flows through the venturi tube, and less is the quantity of air fuel mixture delivered to the cylinders, and hence less is the power developed. As the throttle is opened, more air flows through the choke tube, and the power of the engine increases. The drawback of the simple carburetor is that it provides increasing richness as the engine speed and airflow increases with fully open throttle, because the density of air tends to decrease as the rate of airflow increases. Also, it provides two lean mixtures at low speeds at part open throttle. Why it happens? As you know that the throttle regulates the amount of air flowing through the venturi tube. It also checks the quantity of fuel issuing from the nozzle by regulating the vacuum at the throttle. Now at low engine speed with part open throttle, for the vacuum at the throttle is small, and hence we get two lean mixture. At high engine speed, the vacuum at the throttle is high, and hence we get too rich mixture. The mathematical analysis of the air fuel ratio supplied by the carburetor we will discuss in next few slides. Now, in order to satisfy the demands of engine under all conditions of operation, the following additional systems are incorporated to the simple carburetor: main metering system, idling system, power enrichment by economizer system, acceleration pump system, choke. The main metering system of the carburetor is designed to supply a nearly constant basis fuel air ratio over a wide range of speed and loads. The mixture corresponds approximately to best economy at full throttle. Now the simple carburetor enriches the mixture at high speed. Automatic compensating devices are provided in the main metering system to correct the quality of the mixture. Two devices that can be used for this purpose are the compensating jet that provides increased flow of air through a fuel passage as the mixture flow increases, emulsion tube used for air bleeding. The other devices that are employed to correct the quality of mixture are, that is, tapering or tapered meter pin that can move in and out of the main fuel orifice either manually or by means of some automatic mechanism, changing the quantity of fuel drawn into the air charge. The other one could be the back suction control or pressure reduction in the float chamber, or changing the suction pressure by changing the position or jet in the venturi, or by the use of an auxiliary air valve or port that automatically admits additional air as the mixture flow increases. Compensating jet device. Besides main jet, a compensating jet is provided which is in communication with compensating valve. The compensating valve is open to the atmosphere and gets its fuel supply from the float chamber through a restricting orifice. As the airflow increases, the level of fuel in the valve decreases, thus reducing the fuel supply through the compensating jet. The compensating jet thus contributes in providing lean mixture, whereas the main jet contributes in providing rich mixture, the sum of the two remaining constant. At higher rates of airflow, the compensating jet has been emptied. The air bleeds through the compensating jet so as to provide lean mixture. Emulsion tube or air bleeding device. In modern carburetors, the mixture correction is done by air bleeding alone. In this arrangement, the main metering jet is fitted above 25 mm below the petrol level and it is called a submerged jet, as shown in the figure on the slide. The jet is situated at the bottom of a well. The sides of well have holes which are in communication with the atmosphere. Air is drawn through the holes in the well. The petrol is emulsified. Initially, the petrol in the well is at level equal to that in the float chamber. On opening the throttle, this petrol, being subject to the low throttle pressure, is drawn into the air. Now this continues with decreasing mixture richness as the holes in the central tube are progressively uncovered. Normal flow then takes place from the main jet. Back suction control or pressure reduction method. A common method of changing the air-fuel ratio in large carburetors. The back suction control is shown on the figure on the slide. In this arrangement, a relatively large vent line connects the carburetor entrance, which is shown by the section 1.1. So section 1.1 is showing you carburetor entrance and the section 2.2 is showing you the venturi throttle. So as I told you that a large vent line connects the carburetor entrance, that is point 1, with the top of the float chamber. Another line, that is another pipeline that contains a very small orifice line, connects the top of the float chamber with the venturi throttle, that is at point 2. A control valve is placed in the large vent line. When the valve is wide open, the vent line is unrestricted. The pressure in the float chamber is equal to P1 and the pressure difference acting on the fuel orifice is P1 minus P2. If the valve is closed, the float chamber communicates only with the venturi throttle and the pressure on the fuel surface will be P2. Then P1 will be 0 and no fuel will flow. By adjusting the control valve, any pressure between P1 and P2 may be obtained in the float chamber, thus changing the quantity of fuel discharged by the nozzle. Auxiliary valve carburetor. An auxiliary valve carburetor is shown in the figure on the slide. With the increase of engine load, the vacuum at the venturi throttle also increases. This causes the valve spring to lift the valve, admitting additional air, and the mixture is prevented from becoming overrich. Auxiliary port carburetor. An auxiliary port carburetor is shown in the figure on the slide. By opening the butterfly valve, additional air is admitted and at the same time the depression at the venturi throttle reduces, decreasing the quantity of fuel drawn in. This method is used in aircraft carburetors for altitude compensation. As told you earlier that at idling and low load the engine requires a rich mixture, say about 12:1. However, the main metering system not only fails to enrich the mixture at low air flows but also supplies no fuel at all at idling. For this reason, a separate idling jet must be added to the basic carburetor. The figure is shown on the slide. There is a small fuel line from the float chamber to a point a little on the engine side of the throttle. This line contains a fixed fuel orifice. When the throttle is almost closed, the full manifold suction acts on the outlet to this jet. Moreover, the very high velocity past the throttle plate increases the suction locally. Fuel then can be lifted by additional height up to the discharge point, but this occurs only at the low rates of airflow. As the throttle is opened, the main jet gradually takes over while the idle jet becomes ineffective. The desired air-fuel ratio for the idling jet is regulated manually by idle adjust, which is a needle valve controlling the air bleed. Power enrichment, or you can say economizer system. For the maximum power range of operation, that is, if the load is varying from 75% to 100% of the rated load, there should be a device that allows rich mixture. Rich mixture here we mean that air-fuel ratio of about 13:1 to be supplied despite the compensating leanness. This device is known as meter rod economizer and it is shown on the slide. It simply provides a large orifice opening to the main jet as the throttle is opened beyond a certain point. The rod may be tapered or stepped. Acceleration pump. When we accelerate the engine rapidly, a simple carburetor will not provide the required rich mixture. Rapid opening of the throttle will cause an increased airflow, but the inertia of the liquid flow or liquid fuel will allow at least a momentarily lean mixture just when richness is required for power. To overcome this deficiency, an acceleration pump is provided. The pump consists of a spring-loaded plunger. A linkage mechanism is provided so that when the throttle is rapidly opened, the plunger moves into the cylinder and forces an additional jet of fuel into the venturi. The plunger is raised against the spring force when the throttle is partly closed. Arrangement is provided so that when the throttle is opened slowly, the fuel in the pump cylinder is not forced into the venturi but escapes past plunger or some holes into the float chamber. Now we will discuss about the function of choke. During cold starting period or at low cranking speed and before the engine has warmed up, a mixture much richer than the mixture, that is almost 5 to 10 times more fuel, must be supplied. This is because a large fraction of the fuel will remain liquid in the cylinder and only the vapor fraction can provide a combustible mixture with the air. The rich mixture can be obtained by the use of a choke, which is basically a butterfly type of valve placed between the entrance to the carburetor and the venturi throat as shown in figure on the slide. By partially closing the choke, a large pressure drop can be produced at the venturi throat that would normally result from the amount of air flowing through the venturi. This large suction at the throat will draw large quantities of fuel from the main nozzle and supply a sufficiently rich mixture so that the ratio of evaporated fuel to air in the cylinders is within combustible limits. In some cases, the choke operates automatically by means of a thermostat such that when the engine is cold, the choke is closed by a bimetallic element. After starting and as the engine warms up, the bimetallic element gradually opens the choke to its fully open position. This is basically the Solex carburetor and it is famous for ease of starting, good performance and reliability. It is widely used in Fiat and standard cars and village jeeps. Now if we look into the different parts of Solex carburetor, then this is basically the float chamber indicated by number 1 and connected to it is the main jet. This narrowest cross section is known as the venturi, means the narrowest cross section of the intake manifold is the venturi. This is basically air bleed emulsion system indicated by number 4, and it is the air correction jet. This is orifice or nozzle that is supplying the quantified amount of fuel through main jet. This is basically the butterfly valve indicated by number 7, and indicated by number 8 is the starter valve in flat disc form, and you can see the holes of various size. Now indicated by number 10 is basically jet. Here it is the jet. Shown by number 11 is the throttle valve that is regulating the fuel air mixture going in the engine. This is the starter lever shown by number 12, and here we are having pilot jet, which is used for the starting of engine. Indicated by number 14 is air bleed orifice. This is basically idling volume control screw shown by number 15. This is idle port. It is basically the bypass indicated by number 17. Indicated by number 18 is basically the pump injector, and the number 19 indicates the pump lever. Shown by number 20 is the pump jet, and shown by the number 21 is pump injector. So this was the introduction of the various parts of the Solex carburetor. Now for the normal running. So we are having conventional float in the float chamber. During normal running, the fuel is provided by the main jet and the air by the choke tube or venturi. The fuel from the main jet passes into the well of the air bleed emulsion system. Now air emulsion tube has lateral holes. The air correction jet not only ensures the correct balance of air and fuel automatically, but also calibrates it. The metered emulsion of fuel and air is discharged through the spraying orifice or nozzles drilled horizontally in the vertical standpipe in the middle of the choke tube or venturi. The butterfly valve is shown by the number 7 part. Now if we talk about cold starting and warming, a bi-starter or a progressive starter is provided. A starter valve is in the form of a flat disc with holes of different sizes. These holes connect the starter petrol jet and the starter air jet sides to the passage, which opens into a hole just below the throttle valve at point shown by number 11. Depending upon the position of the starter valve lever, either bigger or smaller holes come opposite the passage. The starter lever which rotates the starter valve is operated from the dashboard control by means of a flexible cable. Initially for starting richer mixture is required, and after the engine starts the richness required decreases. So in the start position, the start control pulled out fully. Bigger holes are the connecting holes. The throttle valve being in closed position, the whole of the engine suction is applied to the starting passage is at point 11. Sucking petrol from the jet and air from jet. The jets and passages are so shaped that mixture supplied to the carburetor is rich enough for starting. After the engine has started, the starter lever is brought to the intermediate position, bringing the smaller hole in the starter valve into circuit, thus reducing the amount of petrol. Also in this position, the throttle valve is partly open so that the petrol is also coming out from the main jet. The reduced mixture supply from the starter system in this situation is however sufficient to keep the engine running till it reaches the normal running temperature when starter is brought to off position, means completely the control has been completely pushed home. Now idling and slow running. From the lower part of the valve of the emulsion system, a hole leads off to the pilot jet. At idling, the throttle is almost closed and hence engine suction is applied at the petrol jet. Fuel is drawn therefrom and mixed with a small amount of air admitted through the small pilot air bleed orifice and forms an emulsion which is conveyed down the vertical channel and discharged into the throttle body past the idling volume control screw. The slow running adjustment screw allows the speed of the engine to be varied. The volume control screw, which permits variation of the slow running jet delivery of petrol, allows the richness of the mixture to be corrected with accuracy. To ensure the smooth transfer from idle and low speed circuit to the main jet circuit without the occurrence of flat spot, bypass orifice is provided on the venturi side of the throttle valve. As the throttle is opened wide, the suction at the idle port is decreased, but suction is also applied now at slow speed opening, which more than offsets the loss of suction at the idle port and thus flat spot is avoided. Acceleration. To avoid flat spot during acceleration, a diaphragm type acceleration pump is provided. This is also known as economy system. It delivers spurts of extra fuel needed for acceleration through pump injector. Pump lever is connected to the accelerator so that when pedal is pressed, the lever moves towards left, pressing the membrane towards left, thus forcing the petrol through pump jet and injector. When the pedal is left free, the lever moves the diaphragm back towards right, creating vacuum towards left, which opens the pump inlet valve and thus admits the petrol from the chamber into the pump. Now we want to discuss the theory of simple carburetor. Now the air from the atmosphere is sucked or inhaled through the carburetor by the pressure difference across it created when the piston moves on its induction stroke, that is suction stroke. The velocity of air increases as it passes through the venturi and reaches maximum at the venturi throat, that is at section 2.2. The pressure also changes and is minimum at the section 2.2 because this is minimum area in the suction track, that is induction manifold, unless the throttle is sufficiently close to provide a smaller area. The fuel is inhaled through the nozzle because of the suction created in the venturi. Now let the height of the fuel nozzle tip be Z meter higher than the flow chamber level. This means that the petrol surface is below top of the jet by Z meter. It is basically done to prevent spilling of petrol when vehicle is stationary. Now this analysis can be done in two ways. One is approximate analysis and another is the exact analysis. In the approximate analysis, we neglect the compressibility of air, but in the exact analysis, we take the compressibility of air into account. Now in the approximate analysis, as I've told you, that we won't be considering the compressibility of air, means density of air has to be assumed to be constant. Now initial velocity of air is assumed to be negligible. Now considering sections at entrance and venturi throat and applying Bernoulli's theorem, we get P1 upon rho A is equal to P2 upon rho A plus C2 square by 2. So P1 is basically the pressure at the entrance and P2 is the pressure at the venturi, that is narrowest cross section. Similarly, C2 is also the velocity at the venturi throat. Now the velocities are in meter per second and density is in kg per meter cube as usual. Pressures are in Newton per meter square. Now the value of C2 is equal to under root 2 into P1 minus P2 upon rho A. So mass of air per second by continuity equation will be given by equation 9.1, where A2 is area of venturi throat in meter square. Now similarly, we apply Bernoulli's equation for the flow of fuel as energy conservation equation. Now here also the initial velocity of fuel has been assumed to be negligible, and rho f is the density of fuel which is assumed to be constant throughout. Now P1 upon rho f is equal to P2 upon rho f plus Cf square upon 2 plus Gz. Now Cf is equal to root 2 into P1 minus P2 minus Gz rho f upon rho f. We also note that due to petrol surface being lower than the top of the jet by Z meter, the pressure difference becomes P1 minus P2 minus Gz rho f instead of P1 minus P2. So the mass of fuel per second mf dot is equal to AF, where AF is the cross-sectional area of the fuel nozzle in meter square, into root 2 into rho f into P1 minus P2 minus Gz rho f, as shown by equation 9.2. Now the fuel air ratio as obtained by 9.3 is shown on the slide. Now taking the coefficient of discharge of fuel nozzle and venturi into account, we write the equation as 9.3a. Now if Z is equal to 0, then air fuel ratio will become as shown by the equation 9.3b. Now as we have derived the expression for the air fuel ratio, we can see that at low airflow, when P1 minus P2 is less than Gz rho f, then there will be no fuel flow. The fuel flow will start only and only when P1 minus P2 is greater than Gz rho f, and the mixture becomes progressively richer. Now with the given value of Z, minimum air velocity at throat to cause fuel flow can be calculated as given by the expression 9.4. Now at higher airflow, when P1 minus P2 becomes large compared to Gz rho f, that is the fraction Gz rho f upon P1 minus P2 becomes negligible, and the air fuel air ratio approaches the expression given by equation 9.5. Now if anyhow reduction in the density of air takes place, that is going to reduce the value of air fuel ratio. It means the mixture becomes richer, and it happens at the condition of high airflow, and then P1 minus P2 is larger, and also C2 is larger, and rho 2 becomes small. It also happens at high altitude when the density of air is too small. Now simple carburetor has a very big drawback, that is the mixture becomes progressively richer with increasing air flows or increasing altitude. The other drawbacks are the carburetor does not supply a rich mixture during idling and low load operation. Richer mixture for starting from cold and extra fuel needed during acceleration. Now we are going to carry out exact analysis for carburetor. Now here we have considered the compressibility of air, that is we have considered the density of air. Now applying steady flow energy equation to section 1 and 2, we get this equation, that is Q minus W is equal to H2 minus H1 plus C2 square minus C1 square upon 2. Now here H1 and H2 are enthalpies at section 1 and 2. Since the process is assumed to be adiabatic, Q is equal to 0, there is no work, that is shaft work, is obtained in the system, and the initial velocity of air is assumed to be 0 or negligible. So C2 becomes under root 2 into H2 minus H1. Now as air is assumed to behave like an ideal gas, H1 is equal to Cp into T1 and H2 is equal to Cp into T2. So C2 becomes under root 2 into Cp into T1 into 1 minus T2 upon T1. Now as the flow process between the atmosphere and Venturi throat is assumed to be isentropic, we can say that relation between temperature and pressure is given by equation 9.7. Now substituting equation 9.7 into 9.6, we get the value of C2 as expressed by equation 9.8. Now the mass flow rate of air is constant from inlet to Venturi throat, and it is given by the expression 9.9, where V is the specific volume. Since the flow process between the atmosphere and Venturi throat is assumed to be isentropic, and if it is irreversible, then it is adiabatic also. So we write the governing equation in terms of pressure and specific volume. And as we know that air or the working substance behaves like an ideal gas, so P1 V1 is equal to RT1. By combining these two equations, we get the value of V2 as shown by expression 9.10. Now substituting the values of C2 and V2 in 9.9, we get the mass flow rate of air as shown by equation 9.11, and shown in the last of the slide, we are having the expression for the air fuel ratio. Now the approximate analysis for mass flow of air given by equation 9.1 can be obtained from equation 9.8. If the pressure drop is sufficiently small, then an approximation can be made in following way. P2 upon P1 raised to power gamma minus 1 upon gamma is equal to 1 minus P1 minus P2 upon P1 raised to power gamma minus 1 upon gamma. This can be written as 1 minus delta P upon P1 raised to power gamma minus 1 upon gamma. Now applying the binomial theorem, we get the expansion of the term, that is P2 upon P1 raised to power gamma minus 1 upon gamma as shown on the slide. Now neglecting the terms delta P square and higher orders, delta P being very small, we get the expression as shown on the second last equation on the slide. Now the value of C2 is shown on the slide as the last equation. As the density of air is assumed to be constant throughout the carburetor, the mass flow rate of air is written as A2 into rho A under root 2 CPT1 into gamma minus 1 upon gamma into delta P upon P1. Now we take rho A inside the root and it becomes rho A square, and we rearrange the terms. Now in the second last equation shown on the slide, we have substituted the value of Cp as gamma R upon gamma minus 1, and finally we get the value of mass flow rate of air as A2 into under root 2 into rho A into P1 minus P2, because in the second last equation inside the second square root gamma upon gamma minus 1 is cancelled by gamma minus 1 upon gamma, and as you know that P1 V1 is equal to RT1, so the first term in the square root, second square root becomes 1. So ultimately we get the last expression. Now aircraft carburetor. An aircraft carburetor operates at varying altitude, whereas automobile carburetor operates at ground level conditions. As you know that with altitude, air density decreases. Therefore, the fuel mixture becomes rich with increasing altitude. So, it is required to provide an altitude mixture correction device in the aircraft carburetors to reduce the amount of fuel with altitude progressively by employing the back suction control or air bleeding or providing a metering pin. Now, ordinary hydrostatic force method is not so useful for condition of engine tilt at angles other than small angles, while aircraft is doing acrobatics. A special system of fuel supply is used to ensure that float chamber or the equivalent reservoir and diaphragm has sufficient quantity of fuel. Another problem that aircraft carburetor encounters is the formation of ice in the choke tube and also in throttle valve due to low ambient temperature. Either an automatic de-icing unit is employed or supply of hot engine oil is circulated around the carburetor barrel and through hollow throttle valve. There are certain drawbacks associated with the modern carburetors. As the induction passes are of unequal lengths and offer different resistance to the flow of air-fuel mixture, the mixture supplied to various cylinders vary in quality and quantity in multi-cylinder engines. Another factor that affects the mixture proportion is the fuel condensation in induction manifold. There are choke tubes, jets, throttle valves, inlet pipe bends in the carburetor, which basically obstructs the free flow passage for the mixture, thus causing loss of volumetric efficiency. Due to various wearing parts present in the carburetor, efficiency of the carburetor lowers after wear has taken place. Another problem, that is freezing. Freezing taking place at low temperatures need to be eliminated. When carburetor is tilted or doing acrobatics, surging of fuel takes place unless special means are employed to eliminate this. One more problem is that backfiring. Due to backfiring, there exists a risk of fuel igniting outside the carburetor, for which flame traps can be provided. What is the basic purpose of substituting the carburation by fuel injection in petrol engines? So that few of the disadvantages that we have discussed may be avoided. In case of diesel engine, fuel is injected directly into the cylinder by injection. But even then, petrol injection method differ from diesel injection method in certain aspects. Now we are going to discuss one of the petrol injection system, that is Lucas petrol injection system. In this system, a single distributor pump is used with a novel metering device which employs a sliding shuttle working in a ported cylinder which is rotated with a fixed ported sleeve. The schematic layout of Lucas petrol injection system for 6-cylinder engine is shown on the slide. The fuel from the main tank is supplied by an electric motor driven gear type pump to a combined fuel metering and control unit. A relief valve returns the excess fuel to the tank and maintains the line pressure at 7 bar. The metering distributor and control unit distributes the required amount of fuel at correctly timed intervals to each of the 6 fuel injectors in turn. The injectors are of the poppet valve type with loading springs, and under the fuel pressure, the valve opens to produce a line spray directed towards the inlet parts as shown in figure on the slide. The fuel is metered by a novel shuttle unit The example of which for a two-cylinder engine is shown in the figure on the slide. It consists of an engine-driven rotor sleeve which has a small sliding shuttle. The shuttle can move between two stops, of which the left hand one is adjustable by the control unit while the right hand stop is fixed. The outer sleeve in which the rotor turns has both inlet and delivery ports. As the rotor turns, the rotor port at the control stop end coincides with the fuel inlet port in the sleeve. Now fuel under pump pressure enters the space between the control stop and shuttle and forces the shuttle to the right, thereby displacing fuel, which is discharged through the rotor and sleeve ports at that end to the injector. A further 180 degree or rotation of the rotor uncovers the fuel inlet port on the right, thus allowing the fuel to enter the rotor and force the shuttle to the left, displacing an identical quantity of fuel to the second cylinder. In this way, the shuttle moves to and fro between the two stops as the rotor is driven round at the half the engine speed, so that at each shuttle movement an accurately metered amount of fuel is displaced and injected into the appropriate cylinder. The quantity of fuel is determined by the position of the control stop, the latter being actuated by the mixture control unit. Now the mixture control unit, the unit which is integral with the metering unit, provides a correct mixture for all driving requirements. It is automatic and is based upon manifold vacuum operated diaphragm and a mechanism which varies fuel according to the load, with appropriate corrections applied for changes in barometric pressure and for cold starting and warm conditions. So this was all for the carburation part. Thank you.